There are three areas which you probably could improve. One is you need to liven up the posters. Choose some colors that are lively. Okay, that's interesting. Secondly, you need to have symmetry on your posters. They should balance out. If it's artwork, it's okay, but most of us are not capable of artwork. Okay, but so without the advantage of being good artists, then you probably need to look at symmetry. And then also, you need to be able to ensure that people can read everything. Okay? And don't put in something just to fill up space, right? There's a temptation to do that. And once again, I think by and large, you all did a very good job. And this is how you learn it, by doing it. Okay. This happened over the last session of the exam, the practice exam, the final. So we'll probably meet in this room at 2:30 rather than the last day or before. So you're all welcome back to make it an earlier session, all right? You have now problem sets. Okay, these are in your book. These are taken directly from your textbook, and they are review sets. And we'll talk about the first set on Friday, and we'll talk about the second set on Monday. And so there won't be any particular lecture session on either Friday or Monday, right? Today I'm going to start taking rolling points, right? So it's like my target date is Monday. You need to have notes back by Monday. Any other things you're wondering about? I'll get your scores back to you for the rest of the homework and so on that you didn't have. Today we wanted to finish up talking about unusual substitution reactions. We have displacement. We classically think of an SN2 reaction as a displacement reaction. And of course it is a very common SN2 reaction. SN2 chemistry is blue powder chemistry. It's a very dependable kind of chemistry. So we think of that very often. Now, last time we looked at the effects of the halogen on the rate of the benzene reaction. We said that the chlorine is the most reactive because it's the first step that's generally the rate step in this elimination followed by addition. Let's look at a couple more examples of this in terms of the a little more inside. We took the example of chlorobenzene and the work that fellow in California and Robbins did with 50-50. We have a scrambling of the carbon-14 particles. Okay. Now, if I take, for example, this kind of compound now, okay, where I have a methyl group here on as a marker, if I treat this with sodium med, okay, plus NH2, and I have ammonia, NH4, this is NH4 plus, and liquid ammonia, minus 33 degrees Celsius, all right? I get two compounds here. I get, if I compound where the amino group winds up on the carbon-bearing halogen, but I also get the meta compound too. Okay. Right. Now, if I go through the various isomers here, if I, for example, took metachlorotoluene, okay, I'm going to wind up with and then I'm going to wind up with 3 isomers, all right? So in every case, we get at least 2 products, and with the metachlorotoluene, you actually get 3 different solutions, don't we? And of course, the consistent pathway here is that of elimination to form benzene, right? And then we have the benzene being attacked by the meta-anion, even though the meta-anion is electron rich in the benzene H as well, right? So, let's take the elimination first. So that if I have, we'll take the do it like this, so we can do it that way. Right? Here's the metachlorotoluene, right? So we will then get attack occurring NH2 minus it can attack at either of the 2 CH bonds that are special delivery, yeah? You're welcome. So, anyway, the imidine is such a strong base here that it actually removes one of the benzoic hydrogens, all right? So, we can have this attacking here. That goes down here, and of course, the chloride leaves as well. Okay? That pathway is going to give us this particular benzene, the CH3. I'm going to have an extra bond here. Now, alternatively, of course, we can remove the other hydrogen. Okay? So alternatively, we can remove this one. This can move in here like this, and again, pick up chlorine. Okay, that's chloride ion, of course. So this is going to give us then, this is going to simply give us then this product here. Or I shouldn't say product, intermediate is what I mean to say, of course. enzymes, aren't we? Okay. And then it's just a matter of these reacting with the meta-anion. Okay. Now here's an electron-rich, strong base, the meta-anion, attacking electron-rich intermediate species of enzyme type. But again, the reason this happens is because of release of strain. Okay. This is a very reactive species. So again, I guess I could use colors all over the place if I wanted to. CH3 and H2 here. We have an electron pair down here. Okay. Plus over here. And H2, CH3 with an electron pair up here. Right? Yep. No. It accounts for the products. Right. The same thing with here plus NH2 minus, again, we can go either the discard or the discard, right? And one piece is going to lead to this structure here, CH3, NH2, minus plus minus. That's how we wind up with 4 different products. And of course, that means that when you acidify it by adding, well, actually the proton, well, this is a good proton transfer. Because the actual anion is going to have negative charge of nitrogen, not on carbon. And that's going to give you then CH3 and H minus, right? etc. Okay, etc. Right? All these are the same thing, right? You put a proton here, or a proton here, or a proton here, and you remove one of the NH ones. And then, of course, when you add the NH4 plus, you get the final product, which is CH3, H2 plus NH3 plus the ortho plus pair. Now, on this basis, you should get twice as much of the meta as you do of either the ortho or the pair. I'm not sure what the percentages are here, okay? In the case if you use sodium mid on meta or value, I'm not sure what the percentages are. Right? But you'd expect to get about twice as much meta as you would have either ortho or pair. Okay? So it's a pretty reasonable pathway. As I said, they've been able to identify the okay, that was elimination. Okay, number 3 is addition. I combine those two steps here. Elimination followed by addition. Okay, any questions about that? Yeah. The methyl group is relatively mild in terms of its electron donating properties, so it doesn't really have a dramatic effect. Now you can have some substituent effects though. If I take this compound, I get only the meta isomer. I get only a trace of the ortho isomer. Now, what happens here is that the first step, the loss of H and Cl, gives us this benzyme. And gives it that benzyme. That's the first step. Yeah. But now, when this reacts with the mid-anion, and H2 minus, okay? Right? These would be the two intermediates, wouldn't they? Okay. Now, the explanation that's given for this is that the oxygen here is exerting an inductive effect. And that's going to tend to stabilize the negative charge when it's on the carbon adjacent to the oxygen. Here we have this, here now is weaker here. So this one is not apparently that important. There's a higher free energy evacuation that's formed that way. All right. So, as I said, the major product is this one. So you do get some directing effects. All right. And you had a couple examples in your homework of enzyme, the usual ones that you had to, in fact, you had to use cyclohexane to case account for all the product, right? Come on, thou shalt account for the product, right? Good. We'll take right from the back talk about some more things. So we had a Cipro, the anthrax.
Ja, ale ma błąd.
Years older. What is the matter?
Wait again.
That's hard.
Yeah, I wasn't there. No. Can you just tape it going to you so you can remember it?
You know, I spent the last period of time in class for the year, I guess you might say, in terms of talking about things. And look at some things of interest in terms of their impact on the environment. First thing I want to just talk about ancient forms and dioxin. All right? A lot of you are going to become homeowners, okay? And parents. I'm sure you will. And so forth. So you'll have to think about your lawn, right? Having a nice lawn, right? I guess on my list, I already said it's moderately high. No. So it means you have to tackle dandelions, right? Although you can make dandelion salt, you can make dandelion wine, right? Well, I don't know, it's got to be your decision, okay? How do you handle dandelions? Use a herbicide, right? And in most dandelion killers of broadleaf plants, the chemical agent is something called 2,4-D. 2,4-D is always okay. And this is for clover and dandelions. I try to dig up as many, I just don't spray. I'm sorry, I'm a chemist, but I don't spray. I dig up my clover and I dig up my dandelions. So, if you want to make 2,4-D, you start out with phenol, right? You treat this with a limited amount of dichlorine, so without a catalyst, of course. And you get 2,4-dichloro phenol, okay? Electrical aromatic substitution. Now, you take this compound and treat it with sodium hydroxide, and CH2 C double bond O Na, okay? Minus plus. What the sodium hydroxide does, of course, you have hydroxide ion, it removes this proton here, so we're going to create the anion here, right? And we're going to make an ether. We're going to make an ether. So here's the salt of 2,4-dichlorophenoxy, long word, right? Acetic acid. That's the salt thereof. Now, generally what you do when you use this in herbicides is you use the acid and use an amine to form a salt. And then you put it into some kind of dispersing agent, probably you're going to put it into water. You make an emulsion in water and spray it. Okay. This is in the form of the acid itself. This is called 2,4-D. Okay? And does it kill dandelions? You bet your life it does. Okay? Does it probably contaminate the groundwater? Yeah, it probably does. So anyway, that led to something called 2,4,5-T. Okay? 2,4,5-T. You probably already know what 2,4,5-T is, right? 2,4,5 trifluoro, right? Okay. That was Agent Orange as well. And this was used where? Where? Vietnam was a defoliant, all these people coming through the jungle. Okay? And so we're going to take away their cover, right? Okay? And, we really, and a lot of veterans from Vietnam came out in terms of problems with a variety of conditions. Now, Ancient Orange is, I guess, a 50-50 mixture of 2,4-D and 2,4,5-D, all right? Okay. So, to make 2,4,5-T, you chlorinate benzene 4 times, all right? You're going to need a catalyst. We use aluminum chloride as a catalyst, all right? So we do it 4 times. Each halogen, of course, is deactivating, and for steric reasons, we get the 1, 2, 4, 5. No. This has a melting point of 139 degrees. It's a crystalline solid, you might expect. Paradichrome is used as a moth repellent, by the way. Yeah. Now, if I take this for sodium hydroxide, methyl alcohol, okay, at 160 degrees Celsius, and this is a addition-elimination type reaction. This is not benzene. Not benzene. Okay? Hydroxide ion goes in with one of the carbons, and only a chloride ion comes back out, doesn't it? So that's how you make the sodium salt 2,4,5, 2,4,5 trichlorophenol, and you make this then into the corresponding acetic acid rhythm, and you have 2,4,5-T. Now there's a problem with that reaction there, okay, of making, okay, this is simply 2,4,5 trichlorophenoxide. And you can make the ether by what's something called Williamson ether synthesis, wouldn't you? But there is a problem. Okay? There is a side reaction here. Okay? The side reaction is this. If I take this is the anion we have over there, right? If I stack it up like this, I'm going to form a tricyclic compound, can I? Right? Absolutely. So what happens is this goes in here, this goes in here, okay? You get addition. The same thing happens here. This goes in here. Okay? That's the addition. And then in the subsequent step, we have elimination, don't we? We have elimination. Okay? So that comes in, and subsequently, this comes out. And so, A, we have elimination. B, we have addition. And here we have elimination. So we form this tricyclic compound. Now, This structure here is called dioxin. Now, if you're going to number this compound, we start out with this being number 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay? So this is 2, 3, 6, 7. Tetrachloro. Now, because the oxygens are in a 1,4 position, we call our tetrachloro dibenzo. That's the benzene rings. Para-dioxin. Or for short, it's called dioxin. For short, it's called dioxin. And that was the topic of Mike's poster session, right? You want to tell us a little bit about dioxin?
What do you want me to go into?
Whatever you want to do.
Well, they're formed by like a variety of different things, like wood burning, the different municipal incinerators, and they're found in like treated wood posts and stuff like that. That's why they had a big deal a couple years ago about treated decks and stuff like that. It's because they have these dioxins in them that kids were playing on these decks and they were getting contaminated by the dioxins. The reason
Because you're playing on what?
on like decks and stuff like that, like decks that are made of treated woods.
Oh, you said jacks or what?
Decks.
Oh, decks. Decks.
Yeah.
We have different pronunciation. Decks. Decks, okay. Wooden decks that you have out back your house. Use treated lumber, which is going to be, you know, the water and the insects and so forth.
Yeah.
So they're worried about kids picking up dioxin from the treated lumber,
Yeah.
which probably contains chlorinated compounds, right?
Yeah. Yeah.
Okay, sure. So,
That in their label, or this one right there, is actually labeled as a carcinogen.
okay, carcinogen.
Yep. And then it has a whole bunch of genetic interactions.
So, one of the things they were very concerned about in terms of usually as the herbicides and defoliants was that the dioxin contained in Agent Orange was responsible for all the problems that the people who fought in Vietnam War have had in subsequent since that time, right? And so it really kind of in a bind here because you like to use incineration to get rid of paper and things like that, right? When we use incineration, you can create dioxin. Dioxin occurs naturally, as you said, in the environment whenever you have forest fire burning and so forth, and that's part of the natural process. So we're kind of in a bind here. That's the genesis of dioxin, how it really first came to people's attention, right? Exactly, sure. Okay, let's take a look at another one, shall we? Now, that's the one I gave you for a handout. Okay. This is Cipro. Okay? So when you hear about dioxin contamination, you know what you're talking about. And so where it comes from. Okay, this is something that Leslie and Rebecca chose for their project, for obvious reasons, all right? And they went on the website. I looked into the Merck Index. The synthesis was part of a patent, and it was also, I think, in a German journal, an Allen, back in 1987. So one probably could have found the synthesis in the journal, but they went on the website and found what you have in front of you, all right? And it's some interesting chemistry. Let's look at the two examples here of nucleophilic aromatic substitution. Shall we? A couple examples here, right there. Yeah. The first one occurs in the middle, over on the left. You take cyclo. I guess not that. No. You go from. Let's see where we're at. Okay. The last two steps are basically addition and elimination types of aromatic, nucleophilic aromatic substitution. Okay. Now, in this step here, you've got this chloro compound, chlorine here, okay? You've got a carbonyl group down here. You've got a C double bond, C in cyclopropyl, yep, amine here, right? You've got a hydrogen here, then you've got an ester group down here, oh, ethyl carbon. So there's our substrate at that point in time. Now, the first thing we do is to treat it with sodium hydride, H minus, right? And so what's going to happen with the hydride ion here? What's the hydride ion going to do here, folks? Laura and Jenny was, yeah, I guess you're saying the same paragraph. Okay. He's going to do what? Think of vapor falling off? H minus? Well, what do you think is going to do, Jim? What do you think they'll do?
Remove the hydrogen.
It's going to remove the hydrogen from the hydrogen. Absolutely, it's almost acidic. Thank you, Jane. Absolutely. So the first step here is going to remove that hydrogen from the nitrogen to create that anion. Okay, so we're going to have here Cl, okay? F, Cl, C double bond O, C double bond O, O ethyl, and then double bond N minus. Okay, now you have to bear in mind that this is conjugated with the carbonyl groups, okay? So we can have this kind of bond equalization going on. So this is going to be able to undergo change in its configuration here. So we're going to be able to do this, Cl, we have F, C double bond O, C double bond C, and we'll put the end over here. Okay, we'll put the cyclopropyl group up here, won't we? And here's the Cl in the, okay? We'll put the H here, the H here, C double bond O, right? Now what's going to happen next in this process? What's going to happen? What's the next step? So the first step is loss of proton. We're going to generate dihydrogen gas, which is a regular gas. Absolutely. Okay. Okay. Now also bear in mind, this is more acidic because, of course, the anion is stabilized by the resonance when you remove the proton. It's more acidic. Now, what's going to happen in the next step here? Danielle and Miriam, what's going to happen next time? What's going to happen next time? It's going to add, we're going to get addition in terms of substitution. So this is going to simply add here. Okay? It's going to add right here. Okay? Going to wind up with this intermediate here. Okay? Cl in. We'll put the cyclopropyl group up here. C double bond C, H, C double bond O, C double bond O, O ethyl, right? And I'll put the minus charge down here, won't I? Okay? Okay? Okay, thumbs up. Okay, fine. Okay. Now, let's just focus on this part of it. Let's just focus on this part of it, okay? And see what's going on here, all right? Now, we're going to have Cl. And Cl in. And we'll just go ahead and do this one. Yeah. Now, That negative charge there is going to be stabilized by the presence of that carbonyl, isn't it? Right? Absolutely. Okay. Now we can draw another resonance form. I keep running out of space here. Okay? We can draw another resonance form in which the negative charge appears on the carbon bearing the fluorine, doesn't it? So I have another resonance form down here, Cl, N, like this, double bond, no, let's get that up. And so I have this arrangement here, don't I? Minus there. Now, is it fluorine going to stabilize that negative charge? Of course it is. So this is why this addition and subsequent elimination goes in. This is the nucleophilic aromatic substitution, addition and elimination, and the presence of the carbonyl group and the fluorine is very important to that because it provides, it lowers the free energy of activation for that process to occur, doesn't it? So that's why that reaction goes. So if we go back now to this species here now, we'll put the negative charge over here on the fluorine, fluorine here, and double bond O, double bond O, right? And now, let me put in the rest of this over there. So that means now, this subsequently does this, doesn't it? Okay, and we have that product will be formed. Okay. And so we have made the heterocyclic ring by doing this, haven't we? We made the heterocyclic ring by doing this. Right? By addition, elimination, of course. Now, the last thing I do is to take a molecule having two nitrogens, okay? And I'm not sure of what the name of this is in terms of it's 1,4-diaza cyclohexane. But I'm not sure what its common name is. Okay? I just didn't get a chance to look it up. Okay? But now, what's going to happen here? Well, we see what happens, don't we? This is going to wind up replacing this, isn't it? And how do we do it? We do it the same way. We do it exactly the same way. Now, why does the nitrogen want to bond to this carbon and not to this carbon? This is okay, but apparently this is not okay. Right? This is not okay. What's the reason for that in terms of structure? What's the reason for that? Yeah.
Carbon that the chlorine is on is para to a chlorine group.
Carbon that the chlorine on is para to the carbonyl and also ortho to the fluorine, isn't it? And both of these are marked effects upon stabilizing that intermediate. Absolutely. Absolutely. Smile if that's how you analyze it. Smile at it, really. As I said, this is enriching chemistry. And we can understand what's going on here. We understand exactly what's going on here. So what does our intermediate look like here? And it looks like this, all right? It looks like this, all right? So we have this intermediate then. Okay, once again, we'll always draw the whole thing out. We'll draw the intermediate with a negative charge on the oxygen, all right? That's what we do. As one of the contributing resonance forms, all right? Double bond O. Okay. So we said the nitrogen comes in here, it's going to have a plus charge now, okay? And we have the citrulline ring here. Okay, and over here we have a chlorine, all right? We've got a chlorine here now, we've got this and this, right? So that shows you how the negative charge now is going to be stabilized by appearing on the oxygen here, and also you can draw a form where it's next to the chlorine, right? Okay. And so once again, what happens? This comes back like this comes back like this, and this comes out like this. Okay. So you're going to wind up with, you have to, of course, remove the proton. So I assume that maybe they add impurity here. Let's suppose they're smart enough to do that. Right? Which I presume they are. All right? They are. Okay. So we'll add some purity here to stop up the HCl that's going here. So they wind up with chlorine here. Oh, you have a measurement here. Plus, and as I said, the last two steps in this synthesis of citral are both nucleotide or aromatic substitution by addition to form of Meisenheimer complex. And then that's cyclohexadienal anion now. Cyclohexadienal anion kicks off the leading group, which in both cases is a beautiful chemistry. Absolutely beautiful. Right? Now, let me just comment a little bit more on those, on the other parts of this, and then we'll take our break, all right? The compound in the upper left-hand corner belongs to what class of compounds? Upper left-hand corner. It's a what? It's an acid chloride. It's an acid chloride. In fact, it's 2,4 dichloral 5-fluoro benzoyl chloride. 2,4 dichloral 5-fluoro benzoyl chloride. And so you're going to simply acylate malonic ester, which you can do. We did that. We had examples of that in the class when we talked about this. So you're using magnesium ethoxide, apparently sodium ethoxide. It doesn't work as well as magnesium ethoxide. I don't know the conditions that they use there. What happened, I don't know in that respect. But you simply acylate the nitrogen on the malonic ester. Because of course the middle CH2 in the diethylenol is relatively acidic, because again the anion is stabilized by the two adjacent carbonyls. The next step is unusual. You're going to simply decarboethoxylation. You can take off the ethoxyl group as well. Okay? So apparently you can take off one of the two ester groups and not touch the other one. And, what the mechanism is for that, we could propose perhaps a mechanism, and so forth. But and again, unless I looked at the thing, but it's apparently acid catalyzed. Okay, and obviously you're going to protonate an oxygen, and ultimately you're going to have fragmentation, removing the one ester group. So now you end up with a simple beta keto ester. Okay. Now, next compound is something called triethyl orthoformate. Orthoformate. Okay. Now, what the ortho means in front of a name, particularly of an acid, the ortho means the fewest double bond oxygen that are present. Okay? Fewest possible double bond oxygens in an ortho acid. Okay? Now, the prime example of this is phosphoric acid. Okay? Now, this you call phosphoric acid. An oxidation state of +5. This compound, which is the result of losing water, okay? This is H3PO4. This is HPO3. These both have phosphorus in a +5 oxidation state, so they are phosphoric acids. The one having the three double bonds options is called metaphosphoric acid. The one that has the fewest amounts of double bond oxygen is called orthophosphoric acid. Okay? So that's what the ortho means. This is the meta compound. These differ in their formula by one or more sets of water. Okay? Now, let's see now. Okay. This is formic acid. This is orthoformic acid. Now, orthoformic acid does not exist as such. Okay? This is formic acid, that's orthoformic acid. Or you can say this is metaformic acid. Now, this is ethylformate. Okay? Now, if I make the derivative of orthoformic acid, I get the compound known as triethyl orthoformate. That's what that compound is. This is triethyl orthoformate, all right? Now, when you run these reactions as you have here, you generally use an acid catalyst, okay? Let's just assume we have H+ for simplicity. Let's assume we have a Lowry-Bronsted rather than a Lewis acid. We can use a Lewis acid though as well. Okay? Now, what is this going to do? It's going to protonate the oxygen, of course. You all know that, right? Now, is this reaction going to proceed further? Yes, it is. Why? Because we have two oxygens now, not just one, but two, that do what? Stabilize the cation, right? So when you have acid around, you're going to have this particular intermediate, O-ethyl, plus, minus, we'll say, ethyl alcohol here. And of course, this is going to have several resonance forces, two of which are going to be really pretty stable. We're going to have HC double bond O ethyl plus O ethyl. And then the positive charge can be on the other oxygen as well, and plus O ethyl. Okay? So what does triethyl orthoformate give you? It gives you this kind of a carbocation, which is a very reactive electrophile. And all when you get this condensation reaction, which gives you the double bond OET. Okay? That's what's going on there. And that's basically a condensation reaction. If you want to balance it, you just simply take the ethyl orthoformate and the beta-keto ester. You take two hydrogens away from the ester, you make the condensation product, you get back 2 molecules of alcohol. That's the stoichiometry going on there. Okay, what's the step where the amine reacts, the cyclopropylamine now reacts? What's going on there? What's going on there? Anybody want to help me along? Who wants to volunteer? Soup, what's going on? The amine, of course, is a what? You know, in the middle line, on the left, now, the cyclopropylamine reacts, right? And you replace the OET by the bond to nitrogen. What's going on there? What's happening now? Andy?
The cyclopropylene is acting as a nucleophile.
The nitrogen with its electron pairs acting nucleophiles attracting that same carbon, right? In the process, what happens? The electron pair rolls up to the what? Carbonyl, isn't it? You all follow that? This is like a micro reaction. This is like a micro reaction. The nitrogen attacks at the beta carbon. It displaces that pi electron pair, which goes on, and only the negative charge winds up on one of the two oxygens, right? Reverses itself, it reforms the carbonyl, the carbon-carbon double bond, and out comes what? OET, doesn't it? Very straightforward condition, yeah? Wow. Okay. That's how they make cyclo. Okay. Now, you have your problem assignments for Friday. I'll be here on Thursday evening, of course, to help you out. I really encourage you to go through those as a group. Do these problems. They are review problems, and they will, give you some help in terms of your preparation for the final. All right? Okay.
Maybe that. Taking off the snap. You're okay. I'll watch it. We're going to do it even though it's not clear. Come on, man. Hey, Clark. Hey, what's up? How do you like this weather? Oh, no, it's not nice. Why? It's nice, man. It should be about 70. I know, it could be a little bit. But it makes it easier to study. Clark, I want the answers. Give me a answer. I did up to 55. Yeah, you want to no, He's still running there. Nope, it has run out of charge. So.